Hello everyone! In this video we will continue to examine topic 5.1 electric fields, and in particular we will look at our final example using Coulomb's law. So in this example I want to preface it with a caveat, which is that this is a very challenging example. It is mostly challenging due to its mathematical complexity. And it is the kind of example that, although it is technically in the core syllabus, that you should really only pay attention to, really only sort of delve into if you are looking for a 6 or a 7 at standard level, or you are in higher level, okay? This, in some ways, is a kind of problem that is challenging mathematically, while not adding very much conceptually to the physics. And they're also so long to solve that you usually don't see them on the exam. But it's the kind of thing where if you understand this kind of problem, you are in phenomenal shape for some of the more standard questions that are asked. So, in this problem, we're given 3 charges, okay, 3 different charges here of different magnitudes. And those 3 different charges are different distances apart with an angle specified. They are of different magnitudes, and in this case, there is very little symmetry, which we've used in the last couple of problems, to rely on. So in some ways, we sort of have to brute force this one to calculate the net force on the different charges. And in this example, you were asked to find the net electric force on Q3, although you can see that there is also the task of finding the net electric force on Q2 and on Q1, which I will leave as an exercise to the watcher. Okay, so I'm only going to go through this first one, although the process is in principle the same. All right, so let's find the net electric force on Q3. Here's Q3. Q3 is plus 65 microcoulombs, and Q3 is going to feel a force both from Q2 and from Q1. Let's consider the direction of that force. Q3 is going to feel a repulsive force from Q2 because they're both positive. That is upwards. That is symbolized by F by 2 on 3. Q3 will also feel an attractive force down and to the right due to Q1. That is symbolized here as F by 1 on 3. And then the net force is F3 net, shown with a simple diagram of the vector sum. So we are looking for the magnitude and direction of F3 net. Okay, so how do we get that? All right, well, let's first calculate the lengths, or the magnitudes, of F by 2 on 3 and F by 1 on 3. We do that by applying Coulomb's law, okay, as shown here, KQ, Q over R squared. Now, you need to be careful to get your Q's right, because they're all different in this case. So K is in here, per usual, but then Q2 is 50 microcoulombs, and Q3 is 65 microcoulombs. You divide that by the distance between them, given as 30 centimeters, or 0.3 meters squared, and that gives you a force by 2 on 3 of 330 newtons. Okay, notice that's a strong force, by the way, very strong. And we're still talking about microcoulombs here. The force by 1 on 3 can be calculated in a similar way, except in this case that distance is between R1 and 3, so it's 60 centimeters as shown here, and Q1 is 86 times 10 to the negative 6 coulombs, and Q3, as before, is 65 times 10 to the negative 6 coulombs. Okay. Notice this is just calculating the magnitudes of those vectors. The directions have been implicitly shown so far in our free body diagram. Okay, and that gives us a magnitude for F by 1 on 3 of 140 newtons. Now, next step is to recognize that to get F3 net, you can decompose both F23 and F13 in the horizontal and vertical directions, and then add up the horizontal and vertical directions directly. So here's what I mean by that. I'm going to zoom in. To get F3 net, we're going to observe that the vertical component of F3 net is just the vertical component of F23 minus the vertical component of F13. So when we add them, we take this vector up here, we stick it on top, and the vertical component of F13 is going to be negative, and it's going to go in the opposite direction. So to get the vertical component of our final vector, F3 net, we simply take F23 and subtract the vertical component of F13. Notice that F23 is all in the vertical direction, making our life a little bit easier. So our first step then is to decompose F13 into the part of F13 that is horizontal and the part of it that's vertical. So we go ahead and do that. That's what these two calculations are, x hat and y hat. The horizontal component of F13 is F13 times cosine theta, cosine of 30 degrees. That gives you a value or magnitude of 120 newtons. Notice that y hat here, that vertical component, gives you a magnitude of F13 times sine 30 of negative 70 newtons. Notice that this minus sign comes from considering the direction. Okay, it's down, which in our coordinate system I've chosen to be negative. So that gives us our x component and our y component. And therefore, if we're thinking about F3 net, well, F3 net, notice here that F3 net has a horizontal component that is only the horizontal component of F13. So F13, the horizontal component of F13, is just going to be the horizontal component of F3 net because F23 is completely vertical. So we take that value, and to get F3 net then will just be 120 newtons, the same as F13 cosine 30. The horizontal component of F13 is 120 newtons. But in the y direction, it's a little more complicated. So in the y direction, we have the vertical component of F13, that's negative 70 newtons, and the vertical component of F23, okay, is, as we calculated up here, exactly equal to the total magnitude of F23, which is equal to 330 newtons. So this vertical arrow is 330 newtons, and then it drops to get our net vector by 70 newtons. So 330 newtons minus 70 newtons is 260 newtons, and 260 newtons is the vertical component of F3 net. It's the vertical part of our final vector. So to get the magnitude of our final vector, we simply apply the Pythagorean theorem. We square the x component of F3 net, add it to the square of the y component of F3 net, and take a square root. And that gives us a total magnitude of 290 newtons for F3 net. So now we have that length. But again, if we want that force, we also need to find the direction. We need theta. And so theta, as shown here, can be found using the ratio of the horizontal and vertical components of the net vector. Okay, so our x component is 120 newtons and our y component is 260 newtons. So if we take that ratio here, if we're looking for this angle theta, and we do opposite, that's the vertical component, over adjacent, that's the horizontal component, we have opposite over adjacent, and then we take the arctan of that value, okay? Make sure we're in degree mode. That will give us an angle of 65 degrees. And so our answer for the net electric force on Q3 is 290 newtons at 65 degrees to the horizontal, specified using our diagram. A similar technique can be used to solve the other two problems. But big picture here, big picture, how did we do it? Well, the first thing we did is we used Coulomb's law to get the length of the two original forces, And then we decomposed both forces. F13 was a little bit challenging to decompose because that angle is 30 degrees. F23 didn't really need to be decomposed because it was all vertical to begin with. We add the x components of both F23 and F13, giving us just 120 newtons because F13 is the only contributor. And then in the y direction, 330 newtons minus 70 newtons gives us 260. And then we found the angle and the magnitude using trigonometry and using the Pythagorean theorem. Try out this technique on the next couple of examples. So take a piece of paper and try out finding the net electric force on Q2 and Q1. And the example is done out in the notes.